So let us now take a look at the actual RNN cell and about the structure of such a cell. So remember, the idea is that we have something like the cell in between xt and yt. And we also need to pass on information to the next time point. So we need xt as input, but we also need actually what is symbolized by the red arrow here as an input as well, which comes from the previous time point. And of course, for t equals 0, there is no previous time point. So we have to start with an initial value that we also feed in on the left-hand side. So we actually have two inputs from x and from the previous cell. And we also will have two outputs, y, and also the information we want to pass on to the next cell. So two inputs and two outputs. So let us now, so to say, zoom into the cell and take a look at the cell. So we want to have xt as an input and yt as an output. But you also want to have the information passed on from one time point to another through the different cells, which again is just one cell, but we run it recursively. And usually this information or this quantity is called h, and it's a so-called state vector. And I will show you what it means. So, but just think about it, that some information that goes from time point t-1 to time point t. So again, the idea is if I start at a certain time point x, of course, I don't have a previous value of x, so I have to set up a value h, and therefore I have one more data point or one more increment for h than I have for x and for y. So this state vector can be seen as the memory, if you like, because that's the information we pass on from one cell to the next cell. And if always think about if I say passing on from one cell to the next cell, it is the same cell, but we want to run it recursively in time. So the memory propagates in the system a long time. So the first idea is, of course, we have to add a learnable, so like in a neural network. And therefore, we multiply the input with the weights wx. So this symbol here means multiplication. So it's really a symbol, so that can be just a matrix product, can be dot product, really depends on the case. So, but it just means it's a symbolic multiplication of matrices or vectors or higher dimensional objects. We want to do the same thing with h. So therefore we have a new learnable wh, because it makes sense. It's like an input, and we also have to multiply this with learnables because we want to we want to kind of understand the influence of these so-called states in the state vector on the output. And then we combine both. So we add both informations and we also add a bias. So the structure is in principle like a neuron. And since we want to run this recursively, you can actually see this as a deep neural network. Because when we have a normal time series, we will have hundreds, if not thousands or 10,000s of time points. So we'll run this cell 10,000 times, and that's like a really deep network. In principle, you can see that in this way. But of course, we will have the same weights throughout the different time points. So they will not change. So we add the weighted input from the state vector, so from the previous time point. We add the weighted input from the current time point. So that's the memory on the left-hand side from the previous time point. And then we add the influence from the current time point plus the bias. And what we do next is we add an activation function before we have the actual output. So pretty often that's a tangent hyperbolicus. And then, of course, we have an output, and we want to also add a learnable wy that we multiply with the output in order to generate our prediction w or prediction y. So we have 4 different learnables: Wx, that's the weighted input; Wh, that's the weighted memory, that's the information from the previous time point; Wy, that's the weighted output in order to generate a prediction y, and of course we have the bias. So we have these 4 different learnables, and I also want to emphasize a bit or highlight the tangents hyperbolicus because it has this particular shape where for large values the derivatives are 0. That will be really important for backpropagation because think about it that we have really like something like a deep network. We multiply these derivatives which are close to 0 usually for large values many times, and if you use another activation function, for example like a ReLU, there's really a very poor performance because you don't have this, let's say, compactification so that you multiply large values, large differences with a small inner derivative. Okay, so that's our cell. And therefore we can write down the equation. So we have the weighted input from X plus the weighted information from the previous time step. That's why it's a T minus H. We always should keep this in mind, plus the bias, and that creates the new state vector for the next time point. And we also take this state vector and multiply this with Wy in order to create a weighted output, because we also want to train, of course, the output. So that's actually a relatively simple equation, especially if we compared it to things like a transformer structure. But we still have to take a look at the shape of the different matrices. So what we know for sure, of course, that our time point has the size or the shape 1 times 1. So that's just a number. But then we also want to be flexible with the number of neurons as before. And remember, the size of the weight vector or matrix is determined by the number of neurons, which here is called also number of states, as you see later, because it will also refer to the state vector. So we want to be free with the size of those learnables, Wx, Wh, and also Wy. So therefore, if we, for example, say we have a certain number of states / neurons, and of course, if you have a complex time series, we want to have more of those neurons, then our Wx must be a vector of size n times 1. So n again is the number of neurons / states. If that makes sense, then of course the product is also an object of the size or of the shape n times 1. So therefore the bias also must maintain the same shape. It also must have the shape n times 1. If that's true, and if you put all of that in a tangents hyperbolicus, which just changes the values but does not change the shape of the vectors, the output also must have the same shape. It's also n times 1. So what comes in here has the shape n times 1, and what gets out here also has the shape n times 1, and the same what you have here. So we know already that the output is n times 1. So H, the state vector, has the shape n times 1. If that's true, then of course the previous state vector must have the same shape. So because we just pass it on from one cell to the other one. And if that is true, then WH cannot be just a vector, because if I just multiply this with NP dot, for example, then it would return a scalar. So this actually has to be a matrix, and it has to be an n times n matrix, because if I multiply this now with H, I will get an n times 1 vector back. So just if you look at the different dimensions. And then if we take a look at the output YT, we know YT also has the shape 1 times 1. So if we have HT, and we know already that HT has the shape n times 1, then WY must have the shape 1 times n. So we know the shape of all these learnables. And since we kind of know now what the structure of such a cell is, then we just need to turn it into code. And the idea now is that we want to train an RNN on noisy periodic data. So we first of all, of course, want to import the libraries which are necessary, so NumPy and also Matplotlib for creating plots, of course. And then we want to create an artificial data set. So we want to, in principle, just have a sine curve with some random noise. And then just want to illustrate this, that we have our sinus here. Of course, in such a case, we know that is a sinus, so we know it's an solution is an analytical equation, as an analytical solution, so we would not really need an RNN. It is just an example that you also can see how well the prediction actually works, because here we know what the result would be, and we can directly compare it to our result from the training. So again, we would actually apply an RNN to a time series where we don't really know what the analytical solution is, or where an analytical solution even does not exist. So therefore, let's go back to our user interface and also just create the artificial data set in order to train our RNN on that. So I short that a bit because it's just about creating a simple plot. So we just create our artificial data set, then we have our plot on the right-hand side. And what we want to do is that we want to create two scripts. The one script will be the RNN itself, and the other script will be this part where we just want to test the RNN every time we add a new feature. And therefore, I would recommend to create a new work folder again to create an RNN. And then we just also want to create a subfolder, and we just call it cell or RNN cell. So again, that we just keep everything so that we are able to keep track of the changes in this very simple way and easy way. So we want to just save this. So we save it under, let's call it test RNN, because that's where we're gonna test the RNN. And now we are ready for creating the first cell. So therefore, let me just go back to our PowerPoint, and I want to show you the structure again. So we created this plot and the data set, and now we want to create a cell. So therefore, we will want to open a new script, and we want to set up the RNN as a new class. And of course, we want to add an init where we read in the time series, and where we also want to determine the number of neurons / states. And then, of course, we have to determine a few parameters. So we want to measure the length of the time series. I want to call this capital T. We also want to save the time series. And now we want to start pre-allocating different matrices. So at the end, we want to make a prediction for Y for every time point xt. So therefore, we want to pre-allocate a matrix we want to call Y underscore head. And we want to compare the predictions to the actual values of Y. Then we also want to save how many states / neurons our RNN has. And of course, we have to initialize all the different learnables. And that's what we are going to do now. So therefore, I go just back to our Python user interface. So I will add a new file, and we import NumPy as NP, of course. And we want to set up a new class RNN, and we also want to save this, and let's call it my RNN. Okay, so then we start with our init. And then we have our xt and the number of neurons. So I just say number of neurons because I want to draw this analogy to the earlier lectures, but maybe you can just add a comment where it just say a neurons equals number of states. So it's not, so calling it a number of states is, or calling this quantity states is not an arbitrary choice. So the overall idea comes from a so-called Ising model, which is pretty common or pretty, yeah, has been used in many cases, in particular in quantum mechanics and physics. So if you like, you can just Google that, and I want to just write this down to see Ising model. So what the Ising model actually is not relevant for this course, but just in case if you want to dive deeper and want to know why it's called state and where it actually comes from. So now we want to determine the length of the time series. We don't really know what the actual shape is, but we just assume that the longest extension, so to say, is the number of time points. So it is like 100 times 1 or times 1, 100 as a 100 times 1 or 1 times 100 or something like that. We also want to save xt. And you see, again, I want to keep everything neat and orderly. And then we also want to save y underscore head. And of course, we don't know what y underscore head is. So we first of all need to allocate with NP zeros a matrix, and we know what the size of the matrix is. Itself T times 1 if we want to have many to many. Now maybe you should also write this down. So this is many to many. All right. Then we also want to save the number of neurons / states. And then we also want to reallocate the different matrices. So let me also do that explicitly. So we want to, first of all, define Wx. That is the weight for the input x. And we want to initialize this with random numbers. So let's say NP random and with normally distributed random numbers. The thing is, it kind of matters already for the training process, how you initialize them, and I want to show this later. So that's a very delicate process for RNNs. Okay, so we have then the number of neurons times 1. So that's what we have discussed in the slides. And then we want to create the weight matrix for y. And remember, that was a n times n matrix. And sorry, for h, it was an n times n matrix. And for y, it was a 1 times n matrix. Because remember, the output is y at the time point t, so it's a 1 times 1 matrix. All right, so we have wx, which is n times 1. We have wh, which is n times n. And we have wy, which is 1 times n. So what we still need is the biases. And that is then n times 1 has the same orientation. All right, so if you like, we can of course then compile it. What we also want to do is that we want to keep track of the states. So in principle, we actually don't really need to do that. But for understanding what the RNN does, especially if it does not do what we want it to do, and it's really helpful to look at the states, how they change over time, if we want to find the reason why it's not working, for example. So it's always recommended to save that, and we want to save this in a huge list because it just makes it easier to work with that. So we want to call these list H, and remember the size. So we want to save these vectors in the list, and we do this with NP zeros. And remember the size or the shape of such a vector was n neurons times 1. And we want to do this for all time points. So for t in range self t plus 1. And because we start at t equals 0. All right. So what else do we need? So we can already implement the forward part. So let me just go back to our PowerPoint and to show you again what the mathematical model actually is. So we add the forward part, and in the forward part, we want to feed in the current time point, xt, and also the current state. And we start, of course, with t minus 1. So that's what you see here. And then we just perform or compute the equation that's implied by the structure of the cell. So first of all, we create a so-called, let me just call this output, where I add the product of wx with xt, then the product of wh with h, and then also the biases. And then we put this in our tangent hyperbolicus, and then we also create y hat. So that's essentially just this equation. And we also want to return those three quantities, especially at the beginning, for keeping track of those values and to get some understanding of the RNN. So therefore, let's go back to our user interface and let's take a look at the user interface. Sorry, at our code in the user interface and add the forward part. So we just add the forward part then, and you assume probably that we're also going to add a backward part at some point. So again, we just refer to the own class. We have the current time point xt, and then we have the current state ht minus 1. And then we just compute the equation. So then we have just np dot times self. So we can just copy that. So let's start with the x value. So self x at wx times xt. Then we calculate the dot product of wh and ht minus 1. And we add the biases. Then the whole thing gets into the tangent hyperbolicus, and that creates our ht. So whatever t is, x and age for the same time point, and this is from the previous time point. So that's the information we pass on from the previous time point. And we can now predict y hat at the time point t. So what I always do is that I use capital letters for the matrix or for the vectors, and I use lowercase letters for the elements, and I use the same letters, but just lowercase. So therefore, I always know which variable belongs to which vector or matrix, and I always know that what is a matrix and what is an element of the matrix. So also here we use np dot, and we multiply this with self wy and ht. Also here, we want to keep it all in order, and we want to return this. So we want to return ht y hat, and we also want to return the output because we want to take a look at those values in order to get a feeling for that. All right, so let me just compile it. And now let's go back to our screen where we have our PowerPoint. And now we are ready to run the first test. So we want to start with, let's say, 500 neurons. We import our RNN. We initialize the RNN of the number of neurons in our data set. And then we also want to take a look at those matrices. So y hat, where we have all the predictions, then we have h and t. We also want to keep t. And for the time point 0, we start with an ht at t equals 0. And we initialize the vector or the list h with zeros. So, and that's how we really start, in fact. So h for t equals 0 is a vector just with zeros. So that's our so-called initial state vector. And now we want to apply our cell, which is the forward part now, recursively. So what happens now is that we just take x, t, and put it into our forward part together with the ht. And then we calculate the prediction for y and the next ht. And we use the next ht as an input for the next forward. So that's why the variable name here is the same on purpose, because we want to feed an h from the previous time point into our cell and propagate it to the next. And that will be the input of the cell for the cell in the next time point. So that's the reason why we want to overwrite ht. So we want to apply it recursively. So, and we also want to keep track of the state vectors. We want to monitor how they change, and also we want to keep track of y hat. Of course, that will be, first of all, nonsense because we haven't trained the network yet. However, that's the structure we need. So we just call the forward method recursively by overriding over ht, but by feeding in always the current xt. So therefore, let's go back to our code. And let's go back to our test RNN. So we just determine the number, or just pick the number of neurons. So again, it's the state, but I want to denote this as n neurons to refer to the analogy. So let's start with 500, and then we just import. So from my RNN, import everything, and there will be the RNN. So let me just run this here first, and then we use the autocomplete, just to make sure that's been recognized. So we then have RNN, and we feed in XT and neurons. And that's our RNN. Then we have initialized our RNN. All right. So, and then we should have all different attributes and methods and all the things we need. So we first of all need y hat, this vector. And let's just call it y hat. Then we want to have h. We want to have t. In principle, we can determine t from our xt, but let's just do it like that. And then we have ht, so the initial state vector, which is the first entry in our list. So that's our initial state vector. All right, so let us run this and check whether we get an error message. We don't get any error message. So what is t? So t is 200, makes sense. ht should be just zeros, also makes sense. And this as well. And now we run our forward part recursively. So we just use enumerate so that we can iterate over xt and get the index and the actual value. So we use enumerate of xt. And we just want to make sure, like in the previous lectures, that we have the right shape in order to get the right results for the dot product. So we just reshape it. And then we run our forward part. So we want to have the output. We can just copy and paste what the output is here, that we have it in the correct order. All right, we have the output here, and then we just call the forward part of our RNN. So it's already recognized. Here's our forward part. We have xt, and it asks for ht. So for the previous time, well, that's the ht from the previous time step. And it creates the next ht from the next time step. All right, and let me again just rearrange this a bit that it looks nice. And then we want to keep track of our state vector. And of course, it's always one time point behind, so to say. So we have to add an t plus 1. Because that's the ht at t equals 1. And that's the original ht at t equals 0. So now we have the new ht. At t equals 0, we have these values already. So we started with the zeros. Now we calculate a new ht, but it's for t plus 1. And we also want to save the predictions for y, which is y hat t. And again, we will get nonsense, of course, for the predictions because our network is not able to learn yet. So we apply this recursively, and I also want to illustrate this. Let me just save that, and let me just go back to the PowerPoint. So the key part is this here. So we run the cell recursively over RLT, and that is the equivalent of running the cell throughout the time. So this part here is the part that you really see here in the red frame. And in principle, we just run the loop over the cell, which is equivalent just to calling the cell many times. So what you see here is just unwrapping the loop. It's exactly the same thing. So now we have the structure here, and we want to run it, and we want to plot to predictions, and we also want to plot the state vector. So let's see what we get. And let's go back to our user interface. So let us first of all run the code, and let's see whether we get an error message. So we don't get an error message. We can take a look at y hat. So we just go to y hat. So that's the particular value for one particular type point. And then that's the actual vector. So that's full of numbers. They're all different. So it looks good. And also if we look at the state vector or the different state vectors. So if we just look at H, we have our list, and they are all filled with those arrays, and they have the size or the shape 500 times 1, because we had 500 neurons, and they are all filled up with numbers. So that makes sense. And again, these numbers are meaningless because the network doesn't learn yet. All right, so let us plot all the states. So that's an interesting plot. So let us just evaluate or iterate over H, and then we create a nice plot. So we just say plot NP arrange. Let's plot the first state vectors. So for the first 20 neurons or so. So for the first 20 neurons, and then we go into each age from 0 to 20. So this is for all time points because we're iterating over age, but we only plot for the first 20 neurons because if we would plot for all 500 or so, we would not get a nice plot. So let's just create some like lines, but very thin ones. And also lines that are partly transparent, and you will see why. So we have 20. So we have 20 lines each. So we have a transparency of 95% and opaqueness of 5%. All right. So let me just create a plot now. There's a little error message. So let me just try to fix this error message. Yeah, of course, 2 and 20 do not go well together. All right, so now we have the plot. And that's what I wanted to show you. So for every time point, we now plot the states for the first 20 neurons. And what you see here is in principle just a zigzag pattern, and that's because of the tangent hyperbolicus. Because for large values, it gives you either -1 or +1. Of course, you have some values in between. That's what you can see here, because it's mostly transparent, but you have some values in between. But mainly, you have -1 and +1. That's the idea of the Ising model. Again, we don't need to know all the details about the Ising model here, but creating such a plot is a good idea, and if it looks like this, then it does the right thing at least. So again, most of the values are -1 or +1 or quite close to those two numbers, and you see the zigzag here. So the states are defined as -1 or +1. And let's also just plot the prediction we got. That's probably also interesting. So we just plot our prediction. So we just first of all want to plot xt and yt. So that's the actual data. And we want to plot this together in the same figure with our prediction. And that's then y hat. And we also want to add a legend. So the first entry is y, and the second one is then y hat. And I use LaTeX code. Which is pretty nice that you can just directly use it in Python. All right, so then let's create this plot as well. And you see that, oh, sorry. I actually want to create a legend, but you see it still kind of works, right? So it's actually a good example how flexible Python is. So who knows, maybe I just want to have this just write exactly this plot. Okay, let me just delete this plot. Let me also delete this plot. And now let's add the legend. And here we are. So again, of course, the predictions don't make sense because the network isn't able to learn yet. But in principle, it gives us an idea how to measure our loss. So let me just go back to the slides. Because now we can just look at the difference between the prediction and the true value, and that's our delta y. So that's the change in the loss function, our gradient. And we can calculate something like the mean sum of squared errors by just applying the dot product. That gives us a scalar, and then we also divide it by the length of the time series, which gives us an average value. So therefore, it's the mean sums of squared errors. So it's essentially this equation, and this is our loss function here. All right, so we have our cell. Our cell seems to work, but of course now we want the RNN to be able to learn, and therefore we need to implement backpropagation. And in contrast to the other networks, there's another feature, and it's called backpropagation through time, because we use the cell recursively. And we have to account for that. And that's what we will do in the next chapter when we take a look at backpropagation through time.